I recently moved to California and have a dream of growing wine grapes, but I know nothing about vineyards. So I wondered, could I build a deep learning model that could predict if my property will be suitable for wine grapes? Here's how I did it. To build a data set to classify vineyards versus non-vineyards, I found an awesome site called discovercaliforniawines.com, which has the addresses of all the vineyards in California. For non-vineyards, I grabbed data from Zillow.com for vacant lots of 10 acres or more. Now I realize that this might not be the most accurate model because there might be vacant lots on Zillow that would be perfectly fine at growing grapes. They just don't happen to. So in this case, I've focused on optimizing to ensure I don't have false negatives and I'm okay with some false positives. So here we import the CSV file and you can see what that looks like. So I have my address column and classification of whether or not that address is a vineyard. And then to get detailed information on each address, I use the Google Maps and WeatherBit APIs. Now, if you want to run this yourself, make sure you update the config.py file included here with your own API keys. Sorry, you don't get to mooch off of mine. And then I created some helper functions. So this first one, this lat long, takes an address and then spits out latitude and longitude coordinates. This other one takes in lat long coordinates and then provides an elevation matrix back. So a 5x5 matrix, roughly around 1 square kilometer. And then I grabbed WeatherBit data from their API and limited it down to these core variables here. So, data on wind, precipitation, minimum and maximum temperature, which I thought could be critical for, the knowledge of are there warm days and cool nights, which I've heard are important for growing grapes. And then this GHI, which is essentially solar radiation, and then relative humidity. So this land data takes in our data frame and then uses those helper functions above to get that historical weather data and elevation data. And this essentially creates a number of arrays that are then stored as pickle files. I should note that I didn't grab data for every day of the year. I ran into some rate limit issues with WeatherBit, and also because this data set isn't super large, it's 450 addresses. I was already finding that when I was running it every day, I wanted to do max pooling and sample, so skipping days was a fine way to do that up front and saving some time. So at the end, those vectors are saved as pickle files for our other notebook to train. So we have our train data and then test data at the end. Okay, now we can import the vector variables that we stored as pickles. We'll start with the train data. And here this function just replaces missing values with the mean of that array, each of those arrays. Here we grab the number of dates. So I experimented a little bit with, checking every 5 days or every day for weather data. So we dynamically load that as a variable and that feeds into the shape of our input layers. So the most complex layer is the elevation, since it's a 5x5 matrix. The map coordinates is just latitude and longitude. And then the rest of these, like wind direction, wind speed, etc., is just one value per date. So these will all be, 71 dates long. That's how many we collect, and then one dimensional. Here we create a data frame to store the performance. So, what was the best loss on our validation data and which epoch did we see that on? And then we store all the rest of the variables we set right here. So when we run this, I'll change this right now to 100 just so we have a little more data points. We can plot it over time and just kind of let it run out. And later we'll pick the best epoch to run on. So here we see all the different input layers. The first one being that elevation data. I run a hidden convolutional layer over top of that. And and then have batch normalization with that data, add an activation layer, which we set above. So we're using Elu, I think it's pronounced. I tried Relu. Elu's, for whatever reason, seemed to work slightly better. And then the rest of these are pretty straightforward. Same batch normalization, same dropout. And at the end here, we concatenate all of them. And I formatted it this way so that if we wanted to, we can drop out different variables. The one I was the most concerned was with this x1. That's latitude and longitude data. And I was worried that that was providing way too much weight. For example, that Napa and Sonoma might be like it's just over indexing on any geolocation around that. But when I removed those, it actually did quite well, even without that variable. It only helped slightly. So here, we build our model, print out a summary, then define an optimizer and compile. So I'm going to run this here. And then we'll fit our model. It runs quite fast, as you'll see. Although you can hear my computer fan working away. There we go. Okay. So, keep this one out. It's going a little slower while I'm video capturing. Alright. So we track the performance of each model by unpacking the history that Keras provides. And then we track which of the epochs receive the best loss. And we plot that over time. So here we see they're kind of separated in this particular run. And then here we save it to, so you can see this last run was actually one of our worst with the settings we have here. And then you can run this again and keep on experimenting. And then at the end, we import our test set that's separate from the last variable building Jupyter Notebook. And we test against that. And we see here slightly different. Oh, so that last setting, I got slightly less performance for the correct responses, but still pretty good. So have fun playing with this. You can run as many times as you like, and you can see with all these different runs which ones work well and find the model that works best for you. For this project, I learned that dropout significantly helped the model generalize. Regularization also worked, but required very low values. I was surprised to find out that the model didn't require latitude and longitude input to be fairly accurate. I was worried that it was going to over-index on locations near Napa, Sonoma, etc. My favorite part was that our prospective property was likely to be a vineyard with nearly 80% probability. That's a false positive I'm quite happy with.